Ever wonder what a tree looks like from the hallway? Only the rightmost nodes peeking out? Binary tree right side view, Pattern Mastery 100 is a quick litmus test for your BFS/DFS instincts. Bong interviewers love it because one clean pass nails it in ON, and the explanation shows you can tame levels and visibility like a pro. Let's crush it with basics. We're given a binary tree. From the right side, at each depth we only see the rightmost node. Return a list of those node values from top to bottom. 2 clean patterns. BFS by level, Q. The last node we pop for a level is the one that's visible. DFS, right first, pre-order. The first node we hit at each depth is visible. Both are ON time, OW space, W equals tree width. We'll do BFS. It maps perfectly to one value per level. Plan with BFS. If root is none, return. Push root to a queue. While queue not empty. Record current size equals len queue. Iterate that many nodes. In queue children. The last node in this loop is the right side value for the level. Append it. Handle empty tree. Seed the BFS with root. For each level, walk exactly size nodes. The last one we visit is visible from the right. We've collected the rightmost node per depth. Return the view. Consider the tree in the image. Level order is 1, 2, 3, 4, 5, 6, 7. The rightmost per level is 1, 3, 6, 7. Let's sanity check a couple cases. Each node enters/leaves the queue once ON. Queue holds at most a level's width OW. Here's the final complete solution for binary tree right side view. We do a level order BFS and record the last node of each level, one pass, ON time, and crystal clear to explain. To deepen tree traversal instincts, try binary tree level order traversal, foundational BFS by levels, binary tree zigzag level order traversal, same BFS with alternating order, left side view, mirror of this problem, take the first node per level, vertical order traversal, group by column using BFS/coordinates, and average of levels in binary tree, aggregate values per level. These strengthen your command of queues, level boundaries, and what to capture at each depth. Now, let's break down the first Python solution for binary tree right side view, a clean and intuitive approach that shows us exactly which nodes are visible from the right side of the tree. Here we're setting up the solution class. This is the container LeetCode uses to run the code. Think of it as the outer shell of our solution. This defines the main function. It takes the root of a binary tree and will return the list of nodes you'd see if you were standing on the right side of the tree. Before doing anything, we check if the tree is empty. No nodes means nothing to see from the right side. So if the tree is empty, we immediately return an empty list. Here we create an empty list called res. This will store the values of the nodes we can see from the right side. We create a queue and put the root node inside it. We'll use this queue to process the tree level by level, a method called breadth first search, or BFS. This whole BFS approach runs in ON time because each node is visited exactly once. This loop keeps running as long as there are nodes waiting in the queue. Each round of the loop represents one level of the tree. We capture how many nodes are in the current level. That tells us how many times we should loop before moving to the next level. Now we iterate through all nodes at this level, one by one. We pop a node from the queue. This gives us the next node to process, the same way you'd take the next number from the front of a ticket line. This checks whether we're looking at the last node in this level. The last node is the one you'd see from the right side. If it's the last node of the level, we record its value in the results list. We check if this node has a left child. And if it does, we add that child to the queue so it gets processed in a future level. Then we check if the node has a right child. And if so, we add that as well to the queue. Finally, once all levels are processed, we return the list of right side node values. And that's how this algorithm works. It first sets up a queue for level by level scanning, then captures the last node at each level to build the right side view. Efficient, simple, and elegant. Test case check. Let's walk through it. Input root equals 1, 2, 3, null, 5, null, 4. Let's test our function using this tree input. 1, 2, 3, null, 5, null, 4. This array represents a binary tree in level order form. 1 is the root, 2 is the left child, and 3 is the right child. 2 has a right child 5, left is null. 3 has a right child 4, left is null. We're looking for the right side view, the nodes you would see if you stood on the right side of the tree and looked inward. Quick logic check. From the right side. At level 1, you see 1. At level 2, between 2 and 3, the visible one is 3. At level 3, between 5 and 4, the visible one is 4. So the rightmost values per level are 1, 3, 4. Output 1, 3, 4, and that's exactly what our program returns. 1, 3, 4. It matches the expected output perfectly, which shows the logic is spot on. So, our implementation is correct. The algorithm cleanly captures the rightmost node at each level, producing an accurate right-side view of the tree. We begin by defining the solution class, the standard LeetCode structure where our method will be stored. This defines our main function, right-side view, which will return the list of nodes visible when viewing the tree from the right side. We create an empty list called res. This will hold the rightmost node from each level. Inside our function, we define a helper called DFS. This performs a depth-first search, and because we run in right-first order, it naturally captures the right-side nodes first. This strategy gives us an efficient ON time complexity since each node is visited once. If the current node doesn't exist, we simply return. There's nothing to explore here. This stops the DFS for that path. This line checks whether we've reached a new level of the tree. If the result list has fewer items than the current depth, it means we haven't added a node for this level yet. So we append the current node's value. And since we visit the right subtree first, this guarantees the rightmost node gets recorded. Next, we explore the right subtree. This is the key. By going right first, we ensure the first node we see at each level is the rightmost one. Then we explore the left subtree. These nodes will only be added to the result if no right-side node was found for that level. We start the DFS from the root node at depth 0. Finally, we return the list of right-side nodes we collected. And that's how this algorithm works. It first prepares a list to store visible nodes, then performs a right-first DFS so that each level captures the correct rightmost node. Efficient, simple, and elegant. Test case check. Let's walk through it. Let's test our function using this input. 1, 2, 3, 4, null, 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 5. These numbers represent a binary tree in level order format. 1 is the root, 2 and 3 are its children, and deeper nodes like 4 and 5 show how the left branch extends downward. The null values indicate missing children in the tree structure. Quick logic check. Here's why the solution works. The algorithm is computing the right side view of the tree, the set of nodes you would see if you looked at the tree from the right side. For example, level 1, you see 1. Level 2, on the right, you see 3. Level 3, only 4 appears on this level from the right. Level 4, the node 5 sits alone on the deepest left extension, and from the right view, you still see it because no other node blocks it. So the rightmost nodes at each level form 1, 3, 4, 5. And that's exactly what our program outputs. 1, 3, 4, 5. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully extracts the right side view of the tree. Efficient, accurate, and reliable. The key takeaway? When working with trees, clarity often comes from thinking in levels. Mastering BFS helps you not just see what's in the tree, but what's visible from every perspective. Let's wrap it up. The binary tree right side view problem is one of those interview favorites that tests your mastery of BFS, DFS, and tree visibility logic. It's a clean challenge that reveals how well you understand level order traversal, and whether you can capture exactly what's visible from the right side in just one efficient pass. We're given a binary tree and asked to return the values of the nodes that are visible from the right side, one per level, from top to bottom. There are two clean approaches. You can use BFS, where the last node you see in each level is the visible one, or DFS, where the first node you visit at each depth, going right first, becomes the answer. Both take ON time, but BFS naturally fits the idea of one value per level. We built a BFS loop using a queue. For every level, we processed all its nodes, tracked their children, and recorded the last node of that level as the one visible from the right. That gives us one clear value per depth. No duplicates, no confusion. We ran this in LeetCode, and it worked exactly as planned, efficient, one clean pass through the tree, no runtime errors. The solution passed all test cases, confirming that it correctly captures the rightmost nodes while staying within ON time and OW space complexity.